Okay, everyone. So now we're going to talk about our second differential equation that we're going to focus on that's related to population growth. And this is when growth is limited by what we call a carrying capacity, or basically a boundary that the population cannot get above. Now, this is a great model because it's used a lot of the time in biology, because all animals have a certain amount of resources that they require for life, and eventually the population and the resources should get to a balance where the resources allow for a certain number of population, and the population can stay at that various number, and that's the growth equation we're going to be looking at right here. Now, this is different from exponential growth or decay, because in exponential decay we had an initial value that decayed eventually down to zero, and in exponential growth we have an initial value that just grows without bound and continues to grow, off into in an infinite time away from the starting time. So this is a little bit different. Our growth is limited by this carrying capacity. So the particular equation for logistic growth, I've given three of them right here. And what you'll notice about these three equations is they are all exactly the same. They are the same equation, they're just written in three different ways. Now, do you have to memorize all three of these? Absolutely not. Pick the one that you think is easiest for you to memorize and then just go with that. Or, if you have another way of writing this, so far as mathematically it is the same as these equations, you can use that too. I just expressed them in these three different ways to really show you that for some reason the people in the AP exam think that that they test you on the logistic growth differential equation by quizzing you on showing it to you in many different forms. I don't get it, but that's just what they do. So that's why I'm presenting them to you in these three forms right here. These are the forms that I have most commonly seen them presented in the AP exam. And again, in this case, our variable y is our population. dy dt is the rate of change of our population. Now this constant m, that's our carrying capacity. That's like the limit. I'm going to bring up a graph of what y would look like if we solve this differential equation and show you how that plays a role. And k is this thing called the proportionality constant. Now remember, in the previous video, k was what I called our growth constant. In some textbooks that you look in, they'll call this the rate constant. It's called the proportionality constant here, just to, I think that's important just to distinguish it from the constant that exists in the exponential growth equation, but really it's just another constant. That's all it is. So if we go through and solve this differential equation, it's pretty painful. It requires using partial fractions. You guys actually know how to do it. So if you're bored on a Saturday night or something like that and you got nothing else to do, go ahead and take a crack at this thing and see if you can solve it. But if you do solve it, you should get that the general solution looks something like this right down here, okay? And so you'll notice that if we take the limit as t goes to infinity in this equation, well, e to the negative infinity, that's just going to go to 0. So we end up basically with just m, which is our carrying capacity, and that's what it means. It means as time goes out to infinity, eventually this population is going to settle on that number m, and it is not going to get larger than that. So if we go into Desmos, not into YouTube where we're uploading a video, but if we go into Desmos, this is the plot of this particular function right here. Let's get rid of that B slider. So you'll notice I can change. I have basically three constants in here. K, that proportionality constant, that's usually some number less than 1, so let's keep it right there. Our C value, that just determines kind of it helps determine what the initial population is, but in this case, unlike in the exponential growth model, C is actually not the initial population. The initial population will be right here, M over C plus 1. But so we can vary C, and we can see how that varies a graph, but look what happens when we vary M, we can vary that carrying capacity. And if we look out, obviously, as we go off to infinity, this thing settles on that number m right there, okay? So if we make m go really, really, really high, like if we make it go something out to maybe say like 100, then if we do that, we can see what more of an effect that thing has on it. Now, you might notice, hey, this doesn't make sense. This is saying if we start at a 0 population at negative time, we can also add something to this equation if we wanted to. in this exponent right here, if I add that's why I had that b thing in there. If I had a plus b in here, and then I move that back and forth, now you see our initial population, that point is no longer valid. I would have had to change that, but that's basically how you can move that graph over. So you can look at a population that can be almost zero at a time of zero, then goes through a period of exponential growth, then goes through a period of a slowing of that growth until we eventually hit our carrying capacity. So good thing is this equation right here, you don't have to memorize that thing. I just put this solution up there just so you could see it. What you guys have to know and what you're responsible for in this class is just understanding basically this differential equation. And again, if you have another form that you would like to write it in that you feel like you could memorize a little bit easier, go for it. As long as it's correct, do whatever you want to do. But all you really got to understand mainly is can you put an equation in a form that's like this? And second of all, do you understand that this value m represents the carrying capacity, and what is a carrying capacity? And we just went over that discussing the last graph. So if you know all of those things, you're pretty much good. You know, really the questions that you get on the AP exam on logistic growth, they really don't vary far away from just interpreting this equation and the numbers in it. So let's look at a couple examples of types of problems you could be asked. So let's look at this one. Hey, the fly fishing guide gave a problem about fish. How about that? All right, anyway, so why don't you pause the video and see if you can solve this. Okay, so immediately if you look at these, you should have eliminated one choice right off the bat. And now if this population P is going to be modeled by logistic growth, it has to fit one of those forms that we wrote on the previous page. Now the form that I like to remember, again, this may not be the one you like to remember, but it's the one I like to do, is that first one, which it's K over M times the initial population. I'm using P in this case so we can keep our variables the same, times that carrying capacity minus the current population. I think, sorry, this is current population P, not initial. I think I said initial when I first described that. But anyway, so we just want to make sure, can we get this into a form that looks something like this? Okay, so the first one right off the bat that should tell you, wait a second, this isn't right, is A right here. Why is this not right? Because we have a T in the equation. There's no T in the logistic differential equation. So we can eliminate that one. Now what other ones can we eliminate? Okay, so what do we have right here? If we look at B, B looks like it could be a really good candidate. We get a constant out front and we get a constant minus P over something in the middle. Recall that if we wanted to rearrange the equation that I wrote up here, if let's say, for example, we wanted to multiply that 1 over M all the way through, so I'm talking about this 1 over M on the outside. If we multiply that M through, this equation becomes Kp times 1 minus P over M, and immediately you're saying, hey, wait a second, this one kind of looks like that, but what's the problem with it? The problem is we don't have a P out here. Or even if we distributed that P on the inside, we would have needed a P squared right here and a P right here. So this one, while it's close, it still doesn't match the form of the logistic differential equation, okay? And so let's look at this third one. This third one does match that particular form, okay? Now in this case, I would say this one matches more the form of this one right up here. So if I was going to ask you with option C, what is the carrying capacity in option C, hopefully you should be like, oh, the carrying capacity is 100 because that is the same value that we're referencing right in here, okay? So now I could ask you, what's the proportionality constant? Well, if I asked you that, you know that based on the equation we have right here, this means that K over M must be 0.001, or that K over 100, because we already specified that the carrying capacity was 100, must be equal to 0.001. And so if we multiply that thing by 100, this gets us K is equal to 0.1. Okay, so I could ask you questions like that too. And in fact, that is the exact type of question I'm going to ask you on the next example. So try to pause the video right now and solve this particular problem. All right, if you've done this one, now in this case, it tells us the logistic growth model, but again, if you compared it to the model we had before, everything still matches up. And remember, all you got to do is remember one form of the logistic differential equation. Again, the one I like to remember is K over M P M minus P. Okay, so that doesn't quite look like this form we got right here, but if we distribute this K over M times P into this parentheses, it will start to look like that form. And what we'll end up getting is KP minus KP squared over M. All right, so that tells us in this particular case that, okay, now this meets that form. This says that K is equal to 0.04, and therefore we know that this 0.0004 must be K over M. So if we solve for that, 0.1234 is equal to K, which is 0.04 over M. If we go through and solve for this, we'll get again that M is equal to 100. So actually this was just another version, a very close similarity to the same one we had on the previous problem. And instead of K being 0.1, K was 0.04. But anyway, like I said, this is about it. If you can do this, if you can just interpret the differential equation, that's pretty much all you have to do in terms of the AP exam. With the logistic differential equation. So if you have questions on this, I will hope you will come tomorrow with those and we will go over some more examples in class.